So I'm gonna talk about naturality, Heegaard Floer theory, and then so just a brief setup. So the Heegaard Floer homology is that we have a three-manifold closed-oriented, and we can assign a Heegaard Floer homology. And then initially, this is defined and proved to be a group up to isomorphism by Oshun-Stubble. But it would be nice to have functorality, by which we mean that we have a cobordism from a three-manifold Y1 to another three-manifold Y2, and we want this cobordism to induce some map on the Heegaard Floer homologies. So as the easiest, like the simplest cobordism would be this mapping cylinder when you take a three-manifold Y across I and you glue it to another copy of Y using some self-diffeomorphism of the three-manifold. So at least for these kind of things, we want to have an induced map on the Heegaard Floer homologies. So for this, we would like to have Heegaard Floer homology, and instead of a group up to an isomorphism, we want it to be a concrete group. And also for each diffeomorphism between three manifolds, we hope that we can define a map induced on the Heegaard Floer homology as well. Okay. So we need naturality even for functorality. So it's okay. Okay. Yes. So in order to, so we can first deal with the, let's go back. It doesn't matter. Okay. So just take a closer look at the definition of this Heegaard Floer homology. So given a three manifold, we take a Heegaard splitting, and we can choose a Heegaard diagram for this three manifold. And then we take the torus in the symmetric product, and we run the Lagrangian Floer homology, and we can get the Heegaard Floer homology group. So in the first step, we want to, so actually there are many different choices for this Heegaard diagram. So in order to get an invariant of three manifolds, so first of all, we want that for any given two Heegaard diagrams, we want that that the Heegaard Floer homology group we get from these constructions are actually isomorphic. So we can show that they are isomorphic, and so this Heegaard Floer homology is a well-defined invariant of three manifolds, but only up to isomorphisms. So in order to get a concrete group, we would like to assign, like given any two different Heegaard diagrams, we want to specify a canonical isomorphism between them. And then using this, we want to build a transitive system, and then taking some kind of limit, we can get a concrete group. So this is the first step we want to do. So just kind of what could be difficult in getting this canonical map is that there, in the space of all the Heegaard diagrams, we could have a loop. So like given two diagrams, there are actually many ways to relate them. If you want to define kind of a map, you want to compose them, and then you want to show that different ways of getting it gives you the same canonical isomorphism. So for example, we have this special handle swap loop. So we can first do R prime handle slide on this A arc and get another Heegaard diagram. And then we can slide the beta curves to beta handle slides and get another diagram. So if we look at this gray zone, we can see that they're actually also related by diffeomorphism. So there is this loop, and we want to check that, like doing all this Floer stuff, like we still get kind of commutative things. And indeed, oh yes. So the question is, we want to check that they actually commute when we apply the Heegaard Floer homology. Okay, so indeed it is natural over Z mod 2. So you have Thurston and Zemke show that there exist functors HF hat, HF minus, HF plus, and HF infinity from the category of base three manifolds to F to adjoint U modules. And then, yes, and then isotopic diffeomorphism would induce the same map on the Heegaard Floer homology group. Similarly, we have that for base-oriented links, so that we can actually upgrade that to a factor as well. So in fact, we can unify they unified the proof to balance suture manifolds as follows. So if we have a 3-manifold with, say, many base points, we can first take oriented tangent 2 planes around these points, and we remove a ball around those base points, and then use these tangent planes to give sutures. We can get a balanced suture manifold. And similarly, for this link, we can remove a tubular neighborhood of the link, and for each base point, we can get, we just take a S1 marker on the torus boundary, and then go along the link, along the orientation, and give R plus and R minus, and we can also get a balanced suture manifold. So yes, so they actually, in their proof, they kind of unify things into the suture balance case, and they also show that the suture Floer homology can also be upgraded to a functor. So it satisfies the functorality. Okay, so now if we want to do it over Z, there is this sign issue that I'm going to explain now. So let's say we have two Heegaard diagrams, and then they have the same alpha curves, but their beta curves are related by the the beta equivalence. So which means that these beta curves are related by a sequence of beta handle slides, or we can say like the beta handle body are diffeomorphic real boundary. So in this case, the way they get the canonical isomorphism is by looking at this map. So when this triple are admissible, we can have a map from the tensor product of the Heegaard Floer homology of alpha beta 1, and then beta 1, beta 2 to the Heegaard Floer homology of alpha beta 2. And now, this is done by counting pseudo-holomorphic triangles. And then so, because now beta 1 and beta 2 are beta equivalent, so there exists a unique spin-C structure such that the top grading part of the Heegaard Floer homology of sigma beta 1, beta 2 is actually just Z mod 2. So we can take a generator of theta beta 1 and beta 2 and then put it back into this map. And then we can just say this is the canonical isomorphism that we want, and we check that it forms the transit system, and so on. But the problem over Z is that there are actually two choices. You can have plus or minus. So this is the sign issue over Z. So a way to deal with it is that instead of looking at alpha equivalences, we kind of want to define this canonical isomorphism only for handle slides. And for equivalences, we just take the composition of all the handle slides and somehow show that this decomposition doesn't really affect the map. Okay. So yes, so the main result I want to talk about is that tight Heegaard invariants are strong, which now doesn't mean anything because I didn't say what these are. But this is a generalization of the proof sketch in the appendix of Qianhe, Thurston, Zemke. So they kind of work on the classical Heegaard diagrams with a single base point, and then I'm trying to generalize this to the suture manifolds with suture diagrams. So yeah, so the goal is to kind of review what are strong Heegaard invariants, and then define what are tight Heegaard invariants. And then tight Heegaard invariants is like kind of defined in a way that it could be used in like as a step in establishing naturality over Z. Okay. Yes. So just have some fun. Like we review what are suture diagrams. So a suture diagram is that you have a triple. So you start with a compact oriented surface where the boundary is non-empty. So something like this. You have a genus 3 surface, and you have two boundaries which are marked by the circle. And then these alpha beta are attaching set. So attaching set is a collection of disjoint curves on this surface, which was there just now. So that when you cut the surface along these curves, you get that each connect component contains at least one component from the boundary of the surface sigma. So this is like an example. So we see that if we cut the surface along the purple curves, we get two components, and each component contains one of the boundaries. Okay. So given a suture diagram, we can build a suture manifold as follows. So we can just take the surface cross I, and then we'll attach the attach two handles along the alpha curve and the beta curves on different sides. And then, so on one of the side, we can get something like this. And then like the boundary of the sigma cross I would be the suture. And then this is only one side, and it's called a compression body given by alpha. And then we do the other side and glue them together, we get a suture manifold. Okay, and then for the purpose of the miscibility in the Floer side, we consider isotopy diagrams. So diagrams are taken up to isotopy. So this S, so now we fix a set of diffeomorphism types of suture manifolds we care about. So for example, like the suture manifold that was induced by manifolds with base points, and then like the link induced by the base-oriented links. Or just in the most general case, we can think about balanced suture manifolds where you have this suture diagram, and then like the number of alpha curves and the number of beta curves are the same. So you get a balanced suture. Oh. Okay, so now we finally can define the domain of a strong Heegaard invariant. So this is a graph where the vertices are just isotopy diagram, isotopy suture diagram H, such that the suture manifold built from this diagram is in the set we care about. And also the areas of this diagram is given by a union of different subgraphs. So for example, the isotopy diagram H1 and H2 are connected by an edge if they are related by beta equivalence. So this actually says that the graph GS is a union of four subgraphs, which is G alpha, G beta, G stabilization, G diffeomorphism. Okay. Now, what are strong Heegaard invariant? So a strong Heegaard invariant is a morphism of graphs. So we assign graphs into some category, and then for each arrow, we want it to correspond to an isomorphism in the category C. And also it satisfies four axioms, the functionality axioms, which basically says that it's commutative within G alpha, within the subgraphs. And then the commutativity axiom is like, so we can have a square where the horizontal ones are alpha equivalences, and then like the vertical ones are like stabilization. So this basically says that it is commutative along across different subgraphs. And continuity axioms and Handel swap, which was the example we've seen before. So we want this F also be commutative along that Handel swap loop. Okay, so now what is tie? So remember that we wanted to do things not on the alpha equivalences, but only on the Handel slides. So we would like to consider some smaller graphs to build the transitive systems. So the smaller graph G prime is actually not that different from G, but you just kind of, instead of alpha equivalences, you change it to alpha Handel slides. So this is a subgraph of G. And then, okay, so actually the issue is that G alpha prime and G beta prime, now they usually is not a category. So if you have two Handel slides, if you take composition, usually is not realized by a Handel slide. So this is just a graph. Okay, now we go back and see what is a good definition for tied Heegaard invariant. Is we restrict to this smaller graph, which only consider the Handel slides. So for the axioms, we would like to change commutativity to just replace the equivalences by Handel slides. Now we want to deal with the functionality, but the G prime and then the G prime alpha and G prime beta, as mentioned before, they are not categories. So in order to describe this functionality, we kind of need to specify several particular types of Handel slide loops, and then we glue two cells onto these specify loops in G alpha prime and G beta prime. So there are 6 types of them. So the first one is you get a pair of pens and just pick 2 of them. And we see that they form a handle slide loop where you pick any curve and you slide it, you get the other one, like this. Also, the second type is that you have a Heegaard diagram and you have 2 kind of disjoint pair of pens. And now you wanna do handle slide, and then you can do this, and this. You want them to be commutative because they are really away from each other. And so there are actually 2 types of it. That depends on like whether this middle green thing is actually the same curve. So they are like, so yeah, if they are the same curve on the surface, so it's like you slide it on the 2 different sides of the same curve. And the next one is you have a force puncture sphere, and you're trying to go from the top alpha 1 to the lower alpha 2. And then so you have 2 holes in the middle. So you want to first do this and do that, or you first do this and do that. So you want them to commute. And finally, we have this pentagon where you're trying to go from here and you go here. But then, so that would be this part. So you can go from here and then to here. Wait, I'm confused. Well, anyway, there is a pentagon that is, we want it to be commutative. That's a loop. Okay. Okay, now so we kind of replace the functionality for G prime alpha and G prime beta to require them to be commutative along these handle slide loops. Yes. Actually, there should be one more thing that I forgot to add. That is the stabilization slice. We also want this tie thing to be commutative along that. Okay, so the sketch of the proof is that we already have this morphism of graphs where all the edges is mapped to isomorphism in C. So now we want to extend this invariant to G, the larger graph. So basically, given an alpha equivalence, we want to define a map between them, between the Heegaard Floer homology. So the way is like we just decompose it into a sequence of alpha handle slides. And then because the G prime already defined maps for handle slides, so we just take a composition of it. So it's still an isomorphism. Now, the issue would be if we have 2 different handle slides, then we want them to be inducing the same canonical isomorphism for equivalences. So the way to do it is to say, okay, so if we take like a loop of alpha handle slides, we want to show that they decompose into a sum of handle slide loop. So then, because the type requires the invariant to be commutative along these elementary handle slide loops, then we can see that actually it doesn't matter which path we pick for extending this F prime to a strong one. So yeah, so for that, we just need that this Y2 C delta is simply connected, where the C delta is the suture compression body, which is half of the suture diagram you compress along delta. And then this Y2 is a 2 complex where the vertices are just the attaching sets that are equivalent to delta. So that's just some other attaching sets that gives you the same compression body. And then this is a 2 complex, and then the 1 cells are just are just the handle slide, and then the two cells is the elementary handle slide loop that we attach 2 cells along these loops. So basically, it's kind of like the connected component of the whole G alpha prime, and then we only look at one side, so we forget about the beta for now. So we want to show that this is simply connected. And the proof idea is that, so the first step is we generalize one Reeves result. So we look at another 2 complex, which has more edges and maybe more 2 cells that we attach. And then these two complex, the edges are simple moves. It's not handle slice, but it's like you change one of the curve within the attaching set. So you just you can without doing like a sequence of handle slice. So we can show that this is simply connected. And then the next step is to say, so because the handle slide are simple moves, so we can put, so given any closed edge path, a closed loop in this Y2 C delta, we can actually first decompose it using two cells in X2, because we showed that X2 is simply connected. And then we kind of resolve each simple move into a sequence of handle slide in a minimal way. So we call this minimal resolutions. So we resolve it using minimal resolutions. And then we kind of show that for each two cell in X, we can decompose it into a sum of two cells in Y2. And then we show that any two minimal resolutions are homotopic. So the whole thing just becomes simply connected. Yes, that's what I want to say. Yeah. Yeah, that's it.
Can you apply this to some particular Heegaard invariant?
To some concrete figure.
So we have maps that satisfy those axioms
Gibran and then Mohammed is trying to fix the size using pin structures. So yes, because if we find if the Heegaard Floer kind of using the pin structure, if we can fix the size, then we have the naturality for Heegaard.
Do you know if some loop has a sign issue for the usual fashion? Did you do some computation?
No, I didn't.
Yes. Question? Yeah. Have you ever
The involutive stuff.
Involutive, yes. The involutive theory.
Over Z or
yeah, over Z. Tomorrow we are starting.